Now that we have gathered data and done some simulations, we are going to talk about what that data looks like. And exclusively today, we're going to talk about normal distributions, but we want to be able to know what a skewed left or a skewed right data might look like as well, because they're out there in the real world. Now, if I'm talking about a normal distribution is symmetric about a mean or an average value. So what that would look like visually, if I come over to the right side here, they're going to have something that looks like that, a bell curve. And right in the middle is going to be our average or our mean value. And we'll talk about how that breaks down here in a second. If I have a skewed left data, the bulk of the data is on the right side with a tail on the left. So visually, if I were to draw that, I've got this tail of data that skews out to the left, but then I've got the bulk of the data over on the right side. And so that left side is what's skewing it or causing it not to be normal. And then if I wanted to talk about a skewed right, the bulk of the data is on the left with a tail of data on the right side. So opposite of what we were doing for the skewed left, I would have the bulk of the data over here on the left, and then that tail is going to come out to the right, making those averages a little bit different. So if we were to create some charts off of our data, we could then see those differences between a normal distribution, a skewed left distribution, and a skewed right distribution. Now I want to look specifically back at this normal distribution because there's some things that we can do if we know something is normally distributed. So I can come back up here and I can mark off a couple of spots going left and right. And what these are standard deviations. So if I go a distance between here and here, what that is one standard deviation. Now, a standard deviation is just a measurement of how far apart this data is. So how spread out is it? How compact is it? So the higher the number that is, the more spread out that data is going to be. The smaller the number that is, the more compact that data is going to be. So if I'm looking at a normal distribution, there's some things that we can determine based on these standard deviations. So if I were to look at the amount of data between this first deviation to the left and first deviation to the right, that's going to account for 95% of the data. Excuse me, 68% of the data here. If I were to go out to a second standard deviation, so say I go to this one here, that's going to be the 95% of the data. And if I were to go one more step out here to the third standard deviation, I could then account for 99.7% of the data there. So if I know these different step sizes, I can be able to know how much data lands in between each one of these and then make some predictions about the probability of landing between certain criteria. Now, in order for this to make sense, let's take a look at a scenario here. So let's assume 2,000 students took a test and the scores were normally distributed, meaning if we look at the shape of that data, it's going to look something like this one here, where it's got that symmetry on both the left and right side. We know the mean or the average score was 70 with a standard deviation of 5. Now, the first thing that I do when I look at this is I recognize if something's normally distributed, it's going to have that general bell curve, and I know right in the middle is going to be that average value of 70. Now, if I want to know how spread out this is, I want to look at the standard deviation. So that standard deviation of 5 means that if I come out those couple of steps to the right and a couple of steps to the left, I can determine what these values are going to be. So this first value out would be 75, then I'd have 80, and then I'd have 85. And if I were to go the opposite way, I could say that this would be 65, this would be 60, and then that final one on the left side, 3 standard deviations out, would be a 55. Now that I know these values, I can start to determine the probability of the percentage of scores that land between certain numbers. So first off, on number 1 here, I want to know the percentage of scores that land between a 60 and a 70. Now, if we look back to this normal distribution on the prior board here, I know that 68%, 95%, and 99.7% of data lands between certain standard deviations. So if I come over here, I can fill in those same percentages for my curve. So between 65 and 75, I could say that 68% of the data is going to land between those two values. If I were to go one step up from that, from 60 to 80, so say I go 2 standard deviations out, I know that 95% of the data is going to land between those two values. And if I were to go even one step further than that, out to 55, all the way out to 85, that's going to be 99.7% approximately of the data from these students taking the test. Now, if I look at that value that I wanted to focus in on from 60 to 70 here, we know 95% of the data is going to be between 60 and 80. We only want one side of that. So if I were to try to figure out what percentage of data that is, I would take that 95% and divide it by 2. And that's going to give me that percentage of data on either side of that average. So we'd end up with half of 95, which is going to be 47.5% of the data. So we know that 47.5% of the students should score between a 60 and a 70 based on what we see in this normal distribution. The second one wants us to figure out the percentage of scores between a 60 and an 85. So we start at 60, we go all the way over to 85. We're trying to figure out that percentage of data. Now, one thing I want to look at that I already know is between 60 and 80, here to here, I've got 95% of the data. So really all I need to do is figure out how much lands between 80 and 85, because if I know that, I can then add that on to the 95%, and I would know the percentage of scores between 60 and 85. The question is, how do we figure that value out? Well, if I look up here, I've got a 99.7% and I've got a 95% representing 3 standard deviations out and 2 standard deviations out. If I take the difference between those, if I take 99.7 and I subtract off the 95, that's going to give me the amount of data that lands between 80 and 85 and between 50 and 60. So if I subtract that, I end up getting 4.7. Well, that's going to be both sides. We only want one of those, so if I cut that in half, I end up getting 2.35% landing between either the 80 and 85 or the 55 and 60. So if I come over here to my question, I've got 95% between 60 and 80. I can add to that what we just found, the 2.35%, and I end up with 97.3%. 0.35% of the data lands between those two scores of 60 and 85. So there's a lot of different ways we can do this. We can add up those values, we can subtract them off. It just depends on which sections of this normal curve we're looking at. So for this third one, we want to find the percentage of scores that are above 80. So then what we're looking at, I'm going to use a yellow color here. We want to start at 80 and go to the right. We want everything above that. Well, if we look at this, instead of adding stuff up, maybe we subtract some stuff. I'm going to start out with the 100%, which would include all of our data. And I'm going to subtract off 95% of that data. Now, the reason I want to subtract that off is because I want to get rid of all of the data between 60 and 80, because that's 95% of the data, and we don't care about any of that if we're just trying to go on the right side of 80. Now, that ends up giving us 5%. But that 5% is going to describe from 80 to the right and also from 60 to the left. But we don't want from 60 to the left. So in order to get rid of that side, I'm going to take that 5, divide it by 2, and end up getting 2.5% of the data is going to land to the right side of 80. Now for this final one, we want to talk about how many students scored between a 60 and a 70. Not necessarily the percentage, but how many of them. So if I'm looking at trying to get a number, I need to take the percentage and then multiply by how many we actually had. Now in question number 1, if we look back up here, we already found the percentage of students between 60 and 70 was 47.5%. Now, if I want to figure out the number of students between that, I'm going to take that percentage, 47.5%, and change it into a decimal. So I'm going to move that decimal over. So I've got 0.475, and I want to multiply that by 2,000, because if I want to figure out that percentage, I need to start with the 2,000 and then take the percentage of that. So 0.475 times 2,000 ends up giving us 950 students in that range. So based off of our data, we can expect that 950 students would score between a 60 and a 70, because that's 47.5% of 2,000 students.